What specific problem does your method address regarding AI agents and their ability to self-regulate and request interventions? Can you outline the key challenges you identified in existing research?
My method addresses the problem of AI agents lacking metacognitive abilities, specifically their ability to self-regulate and judiciously request interventions when faced with uncertainty. A key challenge identified in existing research is the difficulty in training intervention-requesting agents within a limited intervention budget, as it requires balancing reward design and policy optimization. Over-incentivizing help requests can lead to premature budget exhaustion, while under-incentivizing can result in agents avoiding help altogether. Additionally, generating annotated trajectories for supervised fine-tuning under budget constraints is resource-intensive, and collecting data for policy training can be prohibitively expensive. My approach proposes an offline and hybrid framework that efficiently collects intervention data in a single pass, addressing these challenges by integrating deep scoring functions with classical tabular reinforcement learning to optimize policy under budget constraints.
How does your proposed method work? Illustrate the three-step process in detail, specifically focusing on the role of the process reward models, PRMs, and tabular reinforcement learning, RL, within your framework.
Our proposed method operates through a three-step process that integrates process reward models, PRMs, with tabular reinforcement learning, RL, to optimize intervention requests under budget constraints. In the first step, we collect state transitions by randomly triggering interventions, which allows us to approximate the environment dynamics and train PRMs for both the base actor and the intervention. The second step involves iterative reward and usage policy search, where we apply tabular dynamic programming, DP, using the PRMs and the transition model to compute optimal trajectories that respect the intervention budget. This step outputs the expected number of help requests from the initial state, iterating until the target budget is reached, without retraining the policy for each reward configuration. Finally, in the third step, we fine-tune the helper policy using the annotated trajectories generated in the previous steps, enabling it to make effective intervention decisions while adhering to the budget constraints. This hybrid approach enhances robustness to off-policy data and significantly reduces the costs associated with intervention calls during training.
Can you provide a straightforward example that illustrates the process of how your algorithm makes decisions about when to request help? Walk through the steps of your method with a hypothetical task.
To illustrate how our algorithm decides when to request help, consider a hypothetical task where an agent must locate a specific object in a cluttered room. Initially, the agent collects state transitions by randomly triggering interventions, which helps build a transition model. As the agent navigates the environment, it uses a process reward model, PRM, to estimate the probability of success at each state. If the PRM indicates a high difficulty level, low success probability, the agent evaluates whether to request help based on a predefined threshold. For instance, if the agent encounters a state where the PRM score suggests a significant challenge, it may decide to invoke a more capable model or a Monte Carlo tree search, MCTS, intervention to assist in selecting the best action, thereby optimizing its chances of successfully completing the task while adhering to the intervention budget. This decision-making process is iterative, allowing the agent to adaptively request help at critical junctures throughout the task.
What empirical results did you obtain with your method? Please specify the performance metrics you used, the success rates achieved, and how these results compare to existing approaches.
Our method demonstrated impressive empirical results, particularly in the situated instruction following SIF task, where we achieved a success rate SR of 62.5% using only 1.0 intervention on average in the S_OBJ split. This performance is notable as it nearly matches that of a policy that employs interventions at every step, which averaged 7.8 to 4.5 interventions. Additionally, our expected intervention usage, EU, closely aligned with observed usage, especially at lower intervention frequencies, indicating effective budget management. In comparison to baselines, our approach outperformed random state selection and PRM state selection methods, achieving higher success rates while utilizing significantly fewer interventions. Overall, our method not only maintained high precision and recall, but also showcased robustness against out-of-distribution states, which was a challenge for the base actor under frequent interventions.
What limitations or drawbacks did you encounter with your method? In what situations might the approach not perform as well, and why?
One limitation of our method is its reliance on the process reward model, PRM, for estimating success probabilities, which may not effectively account for the dynamics of state transitions during multi-step intervention requests. This was evident when we observed that PRM scores were ineffective for state-wise interventions, leading to suboptimal performance due to repeated toggling between the base actor and interventions. Additionally, the base actor's performance deteriorated under high intervention frequencies, particularly when encountering out-of-distribution states, resulting in invalid actions. Situations involving complex, dynamic environments with ambiguous instructions may exacerbate these issues, as the agent's limited training on specific trajectories can hinder its adaptability to unforeseen circumstances. Overall, while our method shows promise, its effectiveness may diminish in scenarios where the agent faces significant variability or ambiguity beyond its training scope.
What future work do you envision building on your study? Are there specific improvements or new applications you wish to explore?
Future work stemming from this study could focus on enhancing the robustness of the intervention requesting framework by exploring more sophisticated models for estimating transition dynamics, which could improve the accuracy of intervention timing. Additionally, investigating the integration of more diverse intervention types and their individual budget constraints could lead to more adaptable and efficient AI agents in complex environments. Another avenue for improvement is the development of methods to better handle unseen states during training, as indicated by the performance discrepancies observed in the trajectory-only approach. Furthermore, applying this framework to real-world applications, such as healthcare or autonomous systems, could validate its effectiveness in high-stakes scenarios where reliable decision-making is critical. Lastly, expanding the evaluation metrics to include long-term task success and user satisfaction could provide a more comprehensive understanding of the agent's performance in dynamic environments.